Hey, hello and welcome to this calculus guide for A-level maths. It's going to be quite a long video, but it should cover the entirety of differentiation and integration, which are both very big topics in the A-level. There'll be lots of examples and important things for you to pick up and memorize. So make sure to go through this carefully and slowly, and hopefully it's helpful. So the first thing I want to just mention, just very quickly, is differentiation. Usually in questions in the A-level, it's very obvious when you're supposed to use it. But just be aware that occasionally they'll throw in things where it's sort of more subtle. So if you ever see the words minimum or maximum, or largest, smallest, etc., just think differentiation as that's usually the way to solve it. And that's what differentiation is for. So for example, if they ask for the minimum of a graph, the maximum volume of a box, the minimum speed, the maximum distance, etc. Okay, so the first thing that's relatively new to the syllabus is differentiation from first principles. Now, these are actually very easy because there's very little you can do, but you do need to know the definition. So the definition of, given a function f of x, the definition of the derivative of x, which we write as f dash of x, is given by this. The limit as h tends to 0 of f of x plus h minus f of x all over h. And you can't actually get any further than that without knowing what specific function you're talking about. And for the A-level, there's not very many that we'll work with. So for example, if we talk about just x to the n, well, let's prove what the f of x is equal to x to the n. Let's find out what the derivative of that is from first principles. Well, that's going to be equal to the lim as h tends to 0 of x plus h to the n minus x to the n all over h. And so we can write that out as x to the n plus n lots of x to the n minus 1 times h, plus a bunch of sort of h squared or higher terms. So I'm going to write that as that, minus x to the n, but just be aware that all the terms, if we expand that bracket out, we'll just have a bunch of h squared or more, and then divide that by h, and we get, we need to keep in the fact that limit as h tends to 0, this, and so then tidying that up, we get the limit as h tends to 0 of, well, the x to the n's cancel. The first term is just going to be x to the n, x to the n minus 1, and then just a bunch of terms with an h in it, at least, because order h squared divided by h will still have an h in it. And so as h tends to 0, that just leaves us with x to the n minus 1. So that's x to the n. And then the only other thing they'll really test you on, for example, is if f of x equals, let's say, sine x. Well, then f dash x will be the limit as h tends to 0 of sine x plus h minus sine x all over h, which is equal to lim h tends to 0 of sine x cos h minus cos x sine h minus sine x all over h. And then what we need to do is use these small angle approximations to say that this is roughly sine x and then cos h at small angles is going to be 1. Just be safe, let's use 1 minus h squared over 2. That's the small angle approximation of cos, minus h cos x minus sine x all over h, which is going to give us, once we've tidied this up, we'll just get to sine x minus sine x times h over 2 minus cos x sorry, that's a plus cos x, and so as h tends to 0, we just get equals cos x. So that's what you need to do for the first principles. Just plug it into that formula every time, and just it should be relatively obvious what to do. Okay. Then we move on to sort of the kinds of functions we'll be dealing with for differentiation, and there's actually very few. So we've got x to the n, this is our f, and our f dash with x to the n is going to be n times x to the n minus 1. So in other words, all you need to remember there is that powers, the power comes down and it decreases by 1. So that's for powers. Separately, we've got e to the x, and that just stays the same. We've got ln x, and that becomes 1 over x. And we've got sine x and cos x, which turn into, so sine x becomes cos x, and cos x becomes minus sine x. And those are the building blocks of differentiation. So just remember effectively the rules for powers, exponential, ln, and I suppose you call this trig. And those are all very easy. But the important thing is that all other functions that we can differentiate can be built out of these functions. And so we do that by learning only 2 rules, the product rule and the chain rule. The product rule is nice and easy because it's effectively just for, if you have a function, let's say y equals u times v times w, e.g. y equals x sine x cos x, so these 3 different things multiplied together. Well, for the product rule, to differentiate, you just work your way through differentiating each one while you leave the others alone. So u dash vw plus u left alone v dash w plus u and v left alone w dash. And so this is a very easy rule. So if you write that down, then you can see that this will be, well, the first one will be sine x cos x plus x cos squared x plus the minus x sine squared x. So that's the product rule. Now, you'll often be given this third rule called the quotient rule, which is given by this, u over v. And this is technically just a special case of the chain rule, which we'll prove later. But if you want to memorize this, it can be helpful as a shortcut. So if y is u over v, then y dash is equal to u dash v minus v dash u over v squared. So write that out. Now that may look more complicated than it is. So for example, if y equals x squared over sine x, then we can say that y dash, well, the top is u, so u dash v, that's 2x times sine x minus v dash, well, that's cos x, so cos x times u, which is x squared, all over v squared, so sine squared x. That's it. So that's how you use the product and quotient rule. And that should be relatively simple. So those questions are nice and easy. The difficult rule that first causes problems for people is the chain rule. And this is an extremely important rule, and it keeps cropping up in lots of different places. And you can sort of loosely sum it up as differentials behave like fractions, e.g. dy dx is equal to dy dt times dt dx. Or another useful version is that dy dx is equal to 1 over dx dy. So just remember that differentials behave like fractions. And that's one version of the chain rule, but you'll more commonly see it in this form. If I have a function that is a composite function, e.g. f of g of x, then to differentiate this whole thing, the resultant function will be this, g dash x times f of dash of g of x. Now, that probably looks quite confusing, but the actual practical way to deal with this is actually extremely simple. So any composite function, all you want to do is start from the inside and work your way out methodically, ignoring the stuff further out until you reach it. If you truly ingrain this habit, you'll find that differentiation becomes extremely easy. So for example, let's just start off with something relatively nasty, ln of sine of e to the x squared. Okay, so hopefully it's clear that this is what we call a sort of a composite function. It's just lots of the functions, the building blocks we have above, just put together. So how do we use this rule, which looks a bit scary? Well, it's actually very easy to do in practice. What you want to do is go all the way to the inside of the function and look for the innermost function you can find. So hopefully in this case, you can spot that the most inside function we've got is x squared. And so all we want to do is just differentiate that and then move out by one layer. So just do it methodically and you should find the differentiation is actually not too bad at all. So if we do that, what's the differential of x squared? Well, it's going to be 2x. Okay, we've done that layer. Now, one more layer deep. So the next function we encounter is e. And so what's the differential of e when we looked earlier? Well, the differential of e is that it stays exactly the same. So it's going to be 2x times e to the x squared, because it just stays the same. Okay, so we've done that. So now let's move one more layer up. Now we're on to sine. Well, what's the differential of sine from earlier? It's cos. So, okay, this is going to be cos e to the x squared. Okay, and then one further layer out, what are we on? We're on ln. So what's the differential of ln according to the building blocks earlier? If you just return to it, it's ln x in 1 over x, so ln goes to 1 over. So we can say that this must be everything over sine e to the x squared. And that's it. That really is it for differentiation via the chain rule. So let's do a few more examples, and then we'll do a couple of composite examples of the product and the chain rule. But hopefully you can see if you just approach it in that way, it's really not that difficult. So if we say y is equal to sine squared x squared plus ln x, for example, well, the first thing I really strongly recommend you do is rewrite any time you see a sine squared, rewrite it as what it actually is, which is, because if you think about it, that's a weird way of writing sine squared. Because what that thing I've written actually means, as you will know, is this. The whole thing is squared. So I really strongly recommend for both differentiation and integration that you rewrite anything like sine squared like this, and you'll see why immediately when we start differentiating it. So if I want to differentiate this, well, what's the most innermost function I can find? It's x squared plus ln x. So that's going to be 2x plus 1 over x when we differentiate it. Then when we move out by 1, it's very clear that we run into sine, whereas if we'd left it in its original form, we sort of run into this sine squared thing, which is just much less, it's just much less obvious that there's this, the next function is sine and the function after that is squared. So that's why I recommend writing it in that form. So we've got 2x times 1 plus 1 over x times by the differential of sine, well, that's just cos x squared plus ln x. And then we move out one layer further and we've got a squared. So what happens when we differentiate a power? Well, that's the power comes down and whatever was inside the brackets left alone, and power decreases by 1. And we're done. So hopefully that should be relatively self-explanatory, and we'll get much more practice of that in other questions as we go through, but that should be reasonably easy to follow. So just make sure you approach differentiation that way. Now, we mentioned earlier that the quotient rule is just a special version of the chain rule, and so a special version of the product rule using the chain rule. So let's prove that. If y is u over v, then we could say that that is just the same as u v to the minus 1. Okay, well, how do we differentiate this? So this is just a product. So what we can do is we can go through, differentiate the first one and leave the second one alone, and then differentiate the second one and leave the first one alone. So plus u v to the minus 1 differentiated. Okay, and so how do we differentiate that v to the minus 1? Well, what's the most inside function? Well, it's v. So we can say that this first bit is left alone, and this is going to be u. Well, what's v differentiated? That's going to be v dash. And then let me rewrite this as this to make it even clearer what I'm talking about. So the furthest inside function is v. So the differential of v is v dash. And then we move one layer out and we say, okay, well, then what's the next function we encounter? And it's to the minus 1. So what happens when you differentiate to the minus 1? We get times minus 1, and then whatever was in the brackets, v, with the power decreased by 1, so to the minus 2. And that is just, we simplify this, u dash over v minus u v dash over v squared, which if we simplify that further is going to be u dash v minus v dash u over v squared, and we've proven the quotient rule. Okay, and so the most nasty things you'll get in differentiation is some sort of composite product and chain example. So you probably won't get anything quite this bad, but let's just say you did. Let's say it was x cos x squared over ln sine x. Something that nasty. Well, what you want to do in this case is just make sure you go through algorithmically and are just very careful about what you're doing. So we know that this is a quotient rule. If we call this whole thing on top u, and this whole thing on the bottom v, and we know that y dash is going to u dash v minus v dash u over v squared. And then all we need to do is work out individually what these things are. So u dash, well, that's just going to be the product rule on top. So that's going to be cos x squared, because the x differentiates and we leave the second one alone, plus the x left alone times the second one differentiated. Well, the innermost function there is an x squared, so we have to, that when differentiated becomes a 2x, and the outermost bit is cos, so we can say that that becomes a minus sine x squared. Okay, so that's our u dash, and then we also need our v dash. Well, our innermost function there is sine x. You could argue it's x, but x differentiates into 1, so let's just, you can ignore that, and so let's just talk about sine x. So that becomes cos x. And then moving one layer out, we get to ln, so that becomes 1 over. So if we differentiate that, that just becomes 1 over sine x. Okay, so that's our v dash. And so now putting it all together, we get y dash must be equal to, well, what is that? That's cos x squared minus 2x squared sine x squared times ln sine x, because that's our v, minus cos x over sine x times our u, which is x cos x squared, all over ln of sine x squared. Now that's obviously absolutely disgusting. We're not really going to get much more useful out of it, but just going to show that differentiation, as long as you're very methodical, really shouldn't be too bad as long as you approach it in the right way. So the important things to know, we can prove all of these. In fact, that's probably a good idea for you to do yourself. If I've got the function tan x, in other words, sine x over cos x, try differentiating that and see what you get. And you should eventually get to the standard result that the differential of tan x is sec squared x once you simplify it. the differential, similarly, sec x, which is 1 over cos x differentiated, that ends up becoming sec x tan x. Cot x becomes minus cosec squared x. Cosec x becomes minus cosec x cot x. And then a to the x, which is slightly trickier, you need to know that a to the x could be rewritten as e to the x ln a, at which point the differential should be relatively obvious because, right, well, e to the x ln a, we differentiate that. What's the most innermost function? Well, it's x ln a. So that differentiates into ln a. And then move one layer out, and what function are we at? We're at e. So that differentiates into itself. We've got e to the x ln a, and we can rewrite that e to the x ln a as a to the x. And so the differential of a to the x ends up being a to the x ln a. Okay, so that's actually it for differentiation in terms of all the knowledge you need. So then, of course, it comes into the question of why do we do this? So the main purpose to use differentiation for is to find stationary points. So if y is equal to f of x, then we can say that at a stationary point, the gradient, which is y dash, is equal to 0. And so you find stationary points by differentiating it and setting it equal to 0 and solving. So for example, y equals x cubed minus 3x squared, actually let's say plus 3x squared plus 3x plus 1. Well, then what's y dash? It's going to be 3x squared plus 6x plus 3, and we set that equal to 0, which leads us to, if we factorize this, x plus 1 squared equals 0. So the stationary points are at x equals minus 1. And then you can find out where the y value is by subbing that back into the original equation. That's all very standard. Everyone knows how to do that. More sort of newer at A level is the idea of classifying stationary points. So if you have a stationary point, it can either be a minimum, a maximum, or it could also be a special point of inflection. Now I'm going to talk about this in a second. So I'm going to call this a special point of inflection. Now, what can we say for all of these? Well, a minimum has, if the minimum occurs at, or the stationary point occurs at x equals a, then we can say that a minimum must have the second derivative at that point be greater than 0. Maximum needs a second derivative at that point less than 0, and a special point of inflection will have f dash dash a at that point equal to 0. So let's see how to apply that classification to our example. So we know that y dash is 3x squared plus 6x, and so y dash dash must be 6x plus 6. And so at x equals minus 1, we get that y dash dash equals 0. Now, this is very important. This does not tell us it is a point of inflection. This suggests point of inflection. And this is a very important distinction that is often overlooked, and we'll discuss it here. So what is a point of inflection? Well, the definition of a point of inflection is a point of inflection is where f dash dash x changes sign. That's very important. E.g., not just where f dash dash x equals 0. because you can imagine a function that goes to 0, but then goes back up, so never actually changes sign. So looking at our example there, what we can say is that at x greater than -1, we've got y dash dash is plus, is positive, and x less than -1, we've got y dash dash is negative. Therefore, therefore y dash dash change sign so it is a point of inflection. But let's see a very simple example of where it's not necessarily going to be a point of inflection. So if y equals x minus 1 to the 4, well, then we get y dash is equal to 4x minus 1 cubed. And if we set that equal to 0, we find that that's at x equals 1 is our stationary points, okay? And y dash dash is going to be 12x minus 1 squared. And so y dash dash of 1 at our stationary point is going to be equal to 0. But if we look at x greater than 1, we've got y dash dash is positive. And x less than 1, we also have y dash dash is positive. Therefore, actually, not a point of inflection. And if we were to draw out the graph of x minus 1 to 4, you should just see it's looks like a quadratic almost. So in other words, it's a minimum. So what you should do when you find y dash dash is 0, you have to check on either side of that point, and if it changes sign, so the rule you actually have to follow for finding points when you think there might be a point of inflection, the rule is if f dash dash changes sign, it's a point of inflection. If f dash dash is positive on both sides, it's a minimum, and if it's negative on both sides, it's a maximum. And so just be aware that when you get that f dash dash is 0, that suggests it could be a point of inflection, but you have to do further investigation like this. Whereas if you get at the point, at the stationary point, that f dash dash is greater than 0, it's a maximum, a minimum. And if you get that it's less than 0, it's a maximum. You don't need to do any more investigation. So that's just a very important point that is often not addressed properly. And one other thing is, if you look at the definition of a point of inflection, you don't need point of inflection does not need f dash of x equals 0. E.g., you can have points of inflection that are not stationary points. For example, on the graph of tan x, you have the graph actually looks like this. It's not a stationary point, but you still have a point of inflection at x equals 0, because a point of inflection looks like where the graph sort of changes its curvature. It's e.g., before x equals 0, it was curving sort of downwards, and then it starts curving upwards and getting steeper. So that's sort of some more important stuff to do with points of inflection that are often not sort of looked at closely enough. Okay, then a couple of easy things. Increasing and decreasing functions. Well, increasing is defined as f dash of x is greater than or equal to 0 for all x. Decreasing, e.g., it's increasing if it's got a positive or equal to 0 gradient for all x. Decreasing, unsurprisingly, less than or equal to 0 for all x. And then you can put strictly increasing or decreasing is just with a strict inequality, not an equal sign, so greater than 0. So, e.g., for what range of k values is y equals x cubed plus 3x squared plus kx minus 3 a strictly increasing function. Well, may look a bit confusing, but what do we say for strictly increasing? Well, we need f dash x to be greater than 0 for all x. So let's find what f dash of x is, or in other words, y dash. Y dash is going to be 3x squared plus 6x plus k. Okay, and if we need this to be greater than 0 for all values of x, let's have a think about what that looks like. Well, this is going to look like a quadratic, and as we vary k, it's going to, if k was big, it could be up here, and if k was negative, it could be down here. And clearly, greater than 0 for all x has to be this kind of graph. In other words, as long as it doesn't cross the x-axis, it's going to be greater than 0 for all x. And what kind of quadratic never crosses the x-axis? Well, it's one without any real roots. So, e.g., need 0 real roots. So discriminant must be less than 0. And the discriminant is going to be b squared, so 36, minus 4 times 3 times k. We need that to be less than 0. And so, just rearranging this, we get that as long as k is greater than 3, the gradient is always greater than 0, and it's a strictly increasing function. Okay. We're actually nearly at the end of differentiation. I just want to pause on sort of the new stuff for a bit, just to mention tangent and normal questions, because these are very common questions and there's lots of marks, and they're actually very, very algorithmic. So as long as you approach them in exactly the same way every time, you should find them very easy. And the reason why they're so easy is because whenever you see the word tangent, what you should think is, okay, it says tangent. What does that tell us? It says at point x equals a, we know that, well, if it's tangent, we know that the curve has equation y equals, the tangent is a straight line, so it's got equation y equals mx to c. And we know at point x equals a, we must have that two things are true. We know that the y values are the same, so the y values of curve and line are equal because they're touching at that point. And we also know y dash values of curve and line are equal at that point. So the way to handle tangent questions is simply to say, okay, well, at point x equals a, we know that the y dash value of the line is just going to be m. And so if we call this 1 and this 2, piece of information 1 will always give you the equation m equals, well, the y dash of the curve at your point A. So that gives us one equation. And then 2, well, you can then usually sub in for I recommend you do this first and sub it in to 2, because it's usually a simpler equation. But the other one also tells us that MA plus C, the y value of our line, is going to be 2y at the value A. And then that's all the information you get. And so that's it for tangent questions. And then for normal questions, it's exactly the same, except for normal, you're going to get that, well, we know that the gradient is perpendicular, so we know that m is minus 1 over just m being equal to y dash a. And so that's, if you just follow that that setup, for all the tangent normal questions, you should find that it just turns into a set of simultaneous equations. So let's just do these questions quickly. So we know that the curve C has equation, well, x e to the 2x, and we want the tangent at the point x equals 2. So we know that C is x, y equals x e to the 2x, and we want the tangent at the point x equals 2. Okay, so using our setup, well, we know that the tangent line has equation y equals mx plus c, and we're talking about at the point x equals 2. So first of all, what do we need for tangent questions? We need to know what y dash is. So using the product rule, we'll get that this is e to the 2x plus x left alone times 2 e to the 2x, just differentiating it. And so summing these in, we know that m must be equal to, well, at x equals 2, y dash, so e to the 4 plus, is it x equals 2 or x equals a half? No, it's x equals a half. So ignore me. Slightly easier in terms of numbers. So e to the 1, oh no, it's just e, plus 1 times e, so 2e. Okay, that's our gradient. And we also know that the y values are equal. So using that, we know that summing our m value in, we've got that 2e times a half, because that's our x value, plus c must be equal to whatever our y value for the curve is. So that's just half e. And so that's told us that c is equal to, I believe, just e over 2 minus e, which is minus e over 2. And so our curve, our tangent line, is y equals 2ex minus e over 2. And just having a look. That looks, yeah, that's the same as our curve. If we just multiply it by 2 and factorize out an e. So you can see they're quite easy. Looking at a slightly harder one, well, okay, so we're told that y equals e to the minus half x, and the normal to the curve at point P, where x equals P, passes through the origin. Okay, so the normal to the curve passes through the origin. So we know actually, instead of y equals mx plus c, it's just y equals mx. And at x equals P, we have that m is equal to, well, it's a normal, so it's minus 1 over, let's just work out what y dash is, minus a half e minus a half x. Okay, and it's at that point x equals p, so it's minus 1 over minus a half e to the minus p over 2, which we can simplify as, I believe, 2e to the p over 2. Okay, and also m times x, so using the fact that, so also setting y values equal, we've got that, well, m is 2e to the p over 2, so we've got 2e to the p over 2 times x, well, x is just p, is equal to the y value of our curve, so that's just e to the minus p over 2. Okay, and that's going to be the solution to the equation. So we've sort of done our standard thing. Now let's see what they want. Show that x equals p is a solution of the equation, that thing. Well, our equation should be the same as that. So if we look at what they've got minus 1, and they haven't got an e to the minus p over 2. So if we just multiply through by e to the p over 2, we get 2e to the p times p equals 1. And subtracting 1, we get 2p, e to the p minus 1 equals 0, which is what they want. Obviously, just relabeling p for x. And so you can see that they're very predictable. Let's do one more. This is considered a 5-star question, so about as hard as, much harder than A-level, and about as hard as these questions get. So, but you can see it's just going to be exactly the same every time. So we know that, let's just writing out what we always use. We know that at x equals, we don't know the point P, so at x equals P, y dash equals M, and y curve equals M E plus C. Right, so the gradients are equal and the y values are equal. So let's just work out what y dash is. Well, y is equal to 2x minus 4 to half. And so y dash is going to be 2 lots times a half, so actually just 1 of 2x minus 4 to the minus a half. Okay, and we also know that the tangent passes through the origin. So what does that tell us? Well, it tells us the tangent doesn't have equation mx plus c, it's just got equation mx, so we can get rid of that plus c. And so now just subbing these things in, we've got that this first one tells us that 2p minus 4 minus m, and also that 2p minus 4 to the half must be equal to m times p. In other words, 2p minus 4 minus a half times p. And so multiplying up by 2p minus 4, we get 2p minus 4 equals p. And so p is equal to 4. So that's our x value. And then find the coordinates of p. Okay, so that's our x value. So we want our y value. And we can get that by subbing it into our curve, which is y equals root 8 minus 4, which equals 4 by root it to 2. So our coordinates are 4, 2. That's it. Okay, so then we get on to sort of the last couple of bits. One thing is called implicit differentiation, and you don't really need to know the proof, but it's worth knowing where this comes from. Implicit differentiation is where if you have a function that's sort of mixed up y's and x's, obviously we need a way to be able to differentiate this, but we won't be able to rearrange this to get it in terms of y. And what implicit differentiation allows us to do is to figure out how to differentiate these functions. So just when you differentiate, you are always differentiating with respect to x. So let's consider how you would differentiate y squared with respect to x. Well, you don't know how to handle that, and you can't actually deal with that. So it's actually a special case of the chain rule, where you just sort of say, well, I need to differentiate those letters, that letter y with respect to y, but I'm differentiating with respect to x. So I need to use the fact that differentiation works on fractions. So I can say that this is the same as dy dx times d by dy of y squared. Now, that may look a bit weird, but just look, notice if the dy's would cancel, and you are just doing the same thing, you're differentiating with respect to x. And then this is just going to be dy dx times, well, d by dy of y squared, which is y. And so that's the proof of implicit differentiation. It's just using the chain rule. But practically, how is that useful? Well, basically, if you notice, what was the effect of differentiating y squared? It just behaved like it was an x, but you've got this sort of extra dy dx multiplier. And that's it. That's all you need to do for implicit differentiation. So let's say it was, find the stationary points. Find the stationary points of this curve. Well, we need to stationary points, we need to differentiate. So if we do that, y squared x, well, that will be, this is the product rule, and let's deal with the y squared first. So y squared differentiates becomes 2y, and then this extra dy dx term, just you always stick in the end. Then the x left alone but then we've also got to use the product rule. So y squared and x differentiated is just 1. So that's that bit done. Plus product rule on x sine y. So that's going to be sine y plus x left alone times sine differentiated. So cos y with an extra dy dx term. And then the rest should be nice and easy. Plus 2x. Now, what you'll often see people do here is when they're finding stationary points, they want to rearrange to get it in terms of dy dx. But you can actually save a lot of time here because you don't need to do that, because we know that stationary points at dy dx equals 0. And so in other words, we can just sub in dy dx equals 0, and that tells us stationary points are where y squared plus sine y plus 2x equals 4. And okay, this question was a bit hard, so we can't really make any further progress on that, but that gives you an idea of how to use implicit differentiation. You see a function that's not in terms of y, just differentiate it like that, and you get dy dx. And you can rearrange to get dy dx, or you can just, if you're finding stationary points, you can just set dy dx equal to 0 to save some time. Okay, so getting towards the end of differentiation now, only a couple of things left. Connect the rates of change using the chain rule. So this is something that some students find very difficult, but the questions actually, as long as you approach them the right way, are not bad at all. And this goes for a lot of difficult questions, but what you essentially want to do is just treat the question as a translation game and just write down everything you are told from the question, and then what you want to get, and then all you need to do is mess around a bit and the answer should fall out. So effectively, connect rates of change is just using the chain rule in the form we saw earlier. So for example, dy dx, we know that that is dy dt times dt dx. That's all there is to it. So I think the best way to illustrate these kind of questions is to go through some examples. So these are some very difficult examples, harder than you get at A level, but you should see the method. So the shape of a bubble remains spherical at all times. So that first sentence actually is very important straight away, because we've got a spherical bubble, and in these questions you really do need to translate everything. So what does the fact that it's spherical tell us? Well, it tells us that the volume is equal to 4/3 pi r cubed, because it's a sphere. So that's what that first sentence tells us. And then we're told that a bubble is formed and its radius is increasing at the constant rate of 0.2 centimeters per second. Okay, so its radius is increasing at the constant rate. So what's that mean? That means the change of the radius over time is equal to, well, it's increasing, so plus 0.2. So that's that sentence done. Then the next part, find the rate at which the volume of the bubble is increasing. Okay, so what does that mean? The question is, what is dv dt, question mark, when the radius equals 8? Okay, and so dv dt is what we want to find. So that's our translation bit done. So now all we need to do is mess around with what we've got to get to the answer. So dv dt, and then looking at what we have, well, we've got dr dt, so that must be equal to dr dt, and then we just use the chain rules to sort of mess around to make it work. So we need to keep that dt on top, on the bottom, we need a dv on top, and we need to cancel that dr. So we put dv dr there. And then the only question is, how do we get dv dr? Well, because we've written down stuff earlier, it's very simple. We've got v here, so if we simply differentiate this with respect to r, we get that dv dr is equal to, well, just 4 pi r squared. And so subbing that in, we know that dr dt is 0.2, and so dv dt is just going to be 0.2 times 4 pi r squared. And so when r equals 8, this is going to be equal to 256 times 0.2, which gives us 51.2 pi. And that's it. Determine the rate at which the volume of the bubble is increasing. So again, what is dv dt? When the surface area of the bubble reaches 64 centimeters. Well, Okay, in other words, we still know that dv dt is this. And so all we need to know is, well, they've talked about surface area. Well, surface area of a sphere is going to be 4 pi r squared. And so if the surface area is 64, in order to find dv dt, all we need to know is what the radius is at that time. So when surface area is 64, to find the radius, we just say 64 equals 4 pi r squared. And then that will give us r. Well, that, in fact, that gives us 4 pi r squared. So we can immediately sub it in and say that dv dt at that time is just equal to 0.2 times 64, which is going to give us what, 12.8. Okay. Calculate the rate at which the surface area of the bubble is increasing. Okay, so ds dt, and we know that sort of doing the same thing as before. We've already got dr dt, that's a nice constant, so we can say that's dr dt times by, well, we need an s on the top, and we need to cancel that r between the two, and so we now need ds dr, but we've already got what s is, so ds dr will just be 8 pi r, and so this is equal to dr, so dr dt is 0.2 times 8 pi r, in other words, 1.6 pi r. And so now what's left is to know, well, what is r at 30 seconds? Well, we know that r is increasing at 0.2 centimeters per second. It starts off at a radius of 0, so at t equals 30, the radius must be equal to 0.2 times 30, which is 6, and so the answer will just be 1.6 pi times 6, which is going to give us 9.6 pi. And so you can see it really is just a translation type thing with these kind of questions. Very similar, next question, a cube. So the very first thing, they've told us we're talking about a cube, so that means that the volume is equal to x cubed, and the surface area is equal to, well, if you think about it, the 6 faces, all of area x squared, so 6x squared. Okay. Show clearly that, well, oh, and they aren't calling it s, they're calling it a. So we'll see that. Show clearly that v equals this. Well, in other words, now we've written those two things down, we just need to eliminate x. So if we rearrange this for x, we get x equals a over 6 to the half. And so v is equal to a over 6 to the half cubed. So a over 6 to 3 over 2, which we get immediately. Okay. The surface area of the cube is increasing at the constant rate of 0.25 centimeters a second. So dA dt equals 0.25. Find in terms of surds the rate at which the volume of the cube is increasing. Okay, dV dt is the question. We have dA dt, so we know we're going to use that. And how do we sort of tidy this up? Well, we need a dV on the top, and we need an A on the bottom to cancel out. So all we need to do is find dV dA, which we've already got V in terms of A from here. So we can say dV dA is going to be, well, that is just 3 over 2 times 1 over 6 times A to the half over 6, over 6 to the half. And we know that dA dt is 1 over 4. So something that in, we get dV dt is going to be, I believe, 3 over 48, just in, A over 6 to the half. And they want to know when its surface area has reached 16 centimeters. Well, so just plugging that in, we get was 3 over 48, 16 over 6 to the half, which is 3 over 48 times 4 over root 6, which is 1 over 4 root 6, or simplified, I suppose that would be root 6 over 24. And that's it. Okay. Last bit of differentiation now. Parametrics, nice and simple. If you are given y as a function of t, x as a function of t, a different function of t, using the chain rule again, how do we find the gradient? Well, regardless of the fact that they're functions of t, the gradient is always going to be dy dx. But in order to do that, we need to find y in terms of x, and that can be tricky. So instead, what we can say is this is, using the fact that they behave like fractions, this is just dy dt over dx dt. And it's that simple. So I'm not going to do any proper examples here because it's very, very easy. But if x is cos 2t, y is sine 2t, then dy dx will be dy dt, which is going to be 2 cos 2t over minus 2 sine 2t. In other words, minus cos 2t over sine 2t. That's it. That's all there is for parametrics in terms of differentiation to find the gradient at a certain point. The final thing I want to mention, that I mentioned all the way back at the start, is you get a hidden differentiation question. So if you just get a question like this, what is the maximum volume of an open-topped square-based box that can be structured using 100 meters squared of material? So the clue that this is differentiation based is the word maximum. And like the other questions, all you want to do is sort of translate it. So, okay, well, we care about the volume of this box. So if we just sort of draw it out, we've got this. And apparently it's square based. So if we say that the base has sides of length x and the height is y, then what can we say? We can say the volume is equal to x squared y. But we've also got 100 meters squared of material. So how do we use that information? Well, we can say 100, because all our material is equal to the surface area of this box. And what's the surface area? Well, the base is x squared, and then we've got 4 sides of xy and no top. So we don't need to worry about adding the top. And now that we've done that, well, differentiation, we want to find the maximum for the volume. So we need to differentiate v. But we can't do that while there's an x and y in there. So why don't we just use this equation below to eliminate one of them, e.g. eliminate y. So this tells us that y equals 100 minus x squared over 4x. And so v is equal to x squared times 100 minus x squared over 4x. Or simplified, that's 25x minus I believe x cubed over 4. Okay, and now that we've got it in that form, very simple to do the differential. So dv dx is equal to 25 minus 3x squared over 4. And we want the maximum. At a maximum, we know the gradient is 0. It's a stationary point. And so that tells us that 3x squared equals 100. So x equals 10 over the square root of 3, and that must be our x, which tells us that our y is, equals, in other words, our height is going to be 100 minus x squared, which is 100 over 3, all over 4 times x, which is 10 over root 3. So that's going to be 200 over 3 times 40, and we can put the root 3 on the top. 5 over 3, I believe. And so the height apparently is half that of the base. And our volume then, finally solving the question, is x squared y, which is going to be 100 over 3 times 5 over root 3, or going to be 500 over 3 root 3. Or if we want to rationalize that, it's going to be 500 root 3 over 9. And so that's how you approach sort of, if you just ever see the word maximum or minimum or something like that in the question, just think differentiation. And it's usually an easy way of getting to the answer. And that finishes the differentiation section of this video. And so now we will move on to the harder bit, which is integration.